I'll get started here. Thanks again. This is now part two of my Antarctic uh, talk here going south, Antarctic data and science. I threw in actually this just a few minutes ago, the picture of the penguins. I realized I'd be breaking a law if I didn't include a picture, at least one picture of penguins in a slideshow or talk about Antarctica. So that gets on the title slide there. Oops. So I'm gonna start out where I ended up last time or close to it. I talked a little bit about Vostok Station being the Russian or Soviet at the time station. That was established as part of the International Geophysical Year, IGY, back in 1957, 58. And then it was kind of formalized along with other stations in the Antarctic Treaty, which I talked about. And the location for Vostok was chosen particularly because it was near, or one of the reasons, near the Antarctic pole of inaccessibility. The US got the South Pole, the Soviets got the pole of inaccessibility. It also is located around the coldest or at the coldest place on Earth. The lowest temperature ever recorded by a thermometer was 89.2, minus 89.2 degrees Celsius back in 1983. So I guess it kind of makes sense that the Soviets, the Russians would be there. They were used to the cold. They also have the coldest place in the northern hemisphere in Siberia, but not quite as cold as this. But there's actually some folks here at NSIC a while ago discovered there actually is colder locations, not far from Vostok, but not right at Vostok. And they derived this. This was Ted Scambos when he was here at NSIC. Now he's at Ceres, and then a host of other folks that were at NSIC, whose name you might recognize back then that collaborated on this. And they actually used thermal imagery from ABHR satellites to get the surface. And they observed temperatures initially as low as minus 92 to minus.
Do you need help? Do you need help getting something for lunch?
Observed in 2010 and 2013 from imagery. There's just a map, and you can see the darker shades there are colder temperatures. Those purple squares are where they actually got images from. And they collected later data. It was as low as minus 9.
Getting lunch?
Yes.
Okay. Love you.
That is likely close to, if not the lowest possible temperature on Earth. The Earth is radiating heat, but the atmosphere absorbs it and then re-radiates it. And so there's kind of a limit on how much heat could be lost to space, and that's going to put a limit on how cold the surface can get. Antarctica is kind of the prime spot. It's high up, the atmosphere is thin. It's obviously cold and dark there, and so it can't probably get much colder than what they've recorded as far as how much heat can be lost. And it comes from these little dips in the plateau, and basically the cold air can kind of settle in there, and you can get these really cold temperatures, just slightly colder than on the kind of the hot little slightly higher elevations. That's a surface temperature, so it's measuring the sensor is measuring the actual radiation, the thermal radiation indicating temperature at the surface, so at the very surface, the skin temperature of the Antarctic ice sheet. But your official meteorological record is generally a 2-meter air temperature, and so there's a little bit of an inversion there. So they calculated if you are at minus 98 right at the surface, you'd be about minus 94 Celsius. So that exceeds the Vostok record. So it is a new record low temperature. However, it didn't make it into the Guinness Book of World Records because the way like the WMO, the World Meteorological Organization, classifies temperatures, it has to be an official in situ thermometer reading. Satellite readings don't count. So there's out of luck at the moment. Ted Scambos I've talked to, he has talked and has been trying to get some support to actually go down there and put a station in and actually get that record. But it's not an easy place to get to. And it's, not cheap, obviously, and so finding support to do that. He hasn't been able to do that yet, but he's hoping still, last I talked. But this is just a image there on the right. The actual AWS is automated weather station, so those are actually the official meteorological stations that can record a temperature. So they're kind of in various places nearby, where they're recording the temperatures, and the colors may be a little hard to see, but once it gets into the oranges and reds, you're at -90. And then there's some of those little circles, which may be hard to see there, where there's been multiple occasions of below -90 or even below -98 degree event. So there's the one there -98.6 actually.
Do you happen to know what decade those stations were put in, installed?
Some of them probably go back even into the 1950s. I don't know offhand.
Wow.
I know, so some of them might be, or at least maybe not those specific instruments, but I think, like the Russians had stations out. But the University of Wisconsin put out a lot of automated weather stations. I think that was more recently, but I don't know exactly when those were put out. Yeah.
Do you know if anything survives in that region?
Not at those temperatures, no.
Thermophiles, like, yeah.
Yeah, there could be, I shouldn't say, there could be some real extreme, but the environment's pretty harsh there, so now that was on the surface. Now we're gonna go to the dark underbelly of Antarctica. Vostok Station, returning to Vostok Station. Again, it was the site of other interesting and strange things field in Antarctica. In 1974, they went out with a ground penetrating radar, like they drive it across or pull it across, and they got strange readings, things that didn't look like they had seen before in Antarctica, that didn't make a whole lot of sense. They didn't really quite understand what they were looking at. And then in 1991, the ERS-1 satellite radar altimeter and SAR went over the site. It confirmed the 1974 data, but it also gave some better indication of what was actually there. And what they discovered was there's actually a lake. There's Lake Vostok underneath the surface. Basically, it's in a depression underneath the ice, where the ice is flowing over, and the weight and the pressure from the ice is so strong that the water stays liquid. It doesn't freeze. There's also some geothermal heat that's insulated, so that helps keep it as well. But it's primarily the pressure. And that's the SAR image there. And you can see kind of the smooth area. That's Lake Vostok. It kind of looks like it might be a lake even almost. And it's about the size of Lake Ontario, and it even kind of looks like Lake Ontario, which is kind of interesting, the shape. And so
how cold is the water? Pressure keeps it from freezing, but any idea what the temperature of the water is?
I believe it's about 27 degrees Fahrenheit, so like -3 or 4 degrees Celsius. That's what I remember seeing. Yeah. So it's below freezing, or below
But
normal
not
freezing point, but because of the right, yeah.
But so it's you see it in the ERS-1 data because you're getting a surface reflection and it's smooth at the surface there?
So yeah, I think so the SAR is getting more of a surface and maybe a little bit below the surface. I don't remember the details on how they connected it with like the ground penetrating to realize that it was actually a lake underneath.
Huh. Okay.
Yeah.
Interesting.
But yeah, that was the thing. I mean, you can see it in the feature there.
Yeah. And what sort of image was that? It's just visible? Yeah.
No, I think that's a SAR.
It's underneath the ground, it's not
That's-
visible.
Yeah,
It's underneath the ground.
Yeah, it's
No, I know, I understand that.
It's
but
a
the
radar.
Reflects off that is if it's ERS-1 SAR, it's reflecting off pretty much the surface, so that's what I'm not.
yeah. So it's a smooth. You do see it in the smooth surface. It's actually, I got under there. It's a radar sat image actually.
Oh.
Yeah. So that followed up with that. Yeah, the radar sat. Yeah. So yeah, I don't know the details of how they connected down to I talked a little bit about more, but basically the base of it can affects the flow at the surface and the topography at the surface. So they managed to, figure out that there's something there's basically water there. So, yeah.
Donna put something on the chat.
If she confirmed the temperature of that water.
Oh, is that what it was? Okay. Okay.
Thank
Thank
you, Donna.
Yeah, thanks, Donna. So yes, there is a lake at Vostok. So water skiing in Antarctica. This was my attempt to try to do an AI image. It didn't really come out very well. Because that doesn't really look very much like Antarctica, but I had the vision of like the fawns on jumping the shark or whatever and with us, but anyways, but I threw it in there. So, but yes, you're not gonna be water skiing there. But Vostok was the first one they discovered, but since then, with more data, they've discovered literally hundreds of these lakes underneath the ice sheet in Antarctica. And they've been mapped with SAR as well as with ISAT and ISAT-2 laser altimetry. And one of the interesting things that they found since the original discovery of the lakes is that these lakes drain and refill in a complex system. They don't just sit there. There's like connections between them, and there's this whole kind of hydrology. And these, so they change. They'll kind of depend as the ice flows over, the pressure changes slightly, and there's little channels that maybe they can squeeze out of, and they go between lakes. And that can actually be observed and has been observed with ISAT and ISAT-2, looking at the altimetry, the elevation level. When the water drains, the ice sinks a little bit. When the water fills up again, it kind of pressurizes again.
Are there fairly frequent low magnitude earthquakes on Antarctica with stuff like this?
I think probably there are. I haven't looked at that specifically, but you do have ice quakes like in
Yeah.
Greenland and in Antarctica, so I wouldn't be surprised if there's some seismic activity that you pick up. Yeah, so you can on the right there is just showing some changes in elevation between I'm not sure exactly what the dates are. Well, the dates are kind of hard to read there, but the tracks that's the elevation from ISAT. Yeah, this was ISAT. And you can see the different color lines are the different elevations, and so you can see that changing there.
In terms of that transition, is it straight from liquid to solid, or is there gases in between?
No, there's no gas
It's just
there.
water.
Yeah, it's all liquid or solid. Yeah. And then this is like a pretty new paper here that just came out. I forgot what the year in, but it's actually 2026. It was a week or two ago. Oh, there it is, 23rd of February. It was only a week ago. Or less than a week ago. So this is out of the process. Yeah, a few days ago. And this is William Sawtoff. He's on the ISAT-2 science team, I believe, along with others in the paper. And so they did some reanalysis and did some better analysis and looked at how these lakes are evolving over the last 15 years. They also use Cryosat-2, which is the ESA radar altimeter, and the satellite altimetry at ATL-15. And they were able to remove some of the biases that had been there, reduce those at least, and then improve the estimates of the lake area and the volume and the height, and then track those changes over time. So these little squiggles and a spaghetti, there's just outlines of the lake. This is the Conway subglacial lake, and showing how much it has varied over the years with the colors corresponding to the year. So you can see there's a lot of variability. And then the blue outline was like the stationary outline that they had originally found. So this is showing how much more detail they can get out of that using the newer data.
I just
And the new
wanted
analysis.
to add Williams, a PhD candidate at School of Mines,
Oh,
and this is his work.
yeah.
And so like, this is his PhD work, which is
Yeah.
amazing.
Okay, thanks. Yeah, I know his name. I don't know if I've actually met him, but I had forgotten that he was at School of Mines. Yeah. Yeah, thanks. That's good. Yeah. Okay, next topic is the Antarctic mass balance and elevation. So mass balance has been tracked. One of the ways is with this GRACE, Gravity Recovery and Climate Experiment, and then its follow-on, which is for FO. And basically, I'm gonna just go to the animation here, which hopefully Okay, maybe start it, there it is. This is really one of the cooler satellite remote sensing instruments that I've seen. It's actually 2 satellites, and the instruments, they're actually not sensing anything directly from Earth per se. They're not sending a signal down, they're not measuring anything directly. They're measuring the distance between their satellites very precisely. And the orbit and the speed of the orbit changes depending on gravity, and which is dependent on mass. And so as the satellites fly over, they'll speed up or slow down depending how much mass there is underneath. And you've got a pair of them. So one's in front and the other's in back. And so when the one goes over a heavier mass, it speeds up and they separate, the distance gets farther, and then the other one will catch up later. And that's what this is showing here. So they're measuring this to like fractions of a centimeter. I think nanometers, I think, yeah. I forgot to double check that, but I'm pretty sure it's on the order of nanometers. So just really tiny amounts, but they can connect that to the mass underneath, and so they can track the mass, and that allows them to look at changes in mass, for example, from ice sheets. And this is the Antarctic mass balance from GRACE and the GRACE follow-on from 2002 to 2005 or 2025. So there's, almost coming up on close to a quarter century time series here. There is a bit of a gap. If I can show that here, right here, where unfortunately GRACE stopped operating in 2017, and then they didn't get GRACE follow-on launched until 2018. So there's about a year gap there. And this is really unfortunate. I've talked about this before, where you want to intercalibrate between the satellites. And ideally you'd have both of them flying at the same time, taking the same measurement. And then the difference is, that's a calibration difference and you can adjust. So there's a little bit of uncertainty there, but the trend is really pretty clearly strongly downward, especially at least up until about 2021 or so. And it's been somewhat flat since then, which is kind of interesting. And the reason for that is more, not so much that the loss is slowing down, but that there's been more snow. And so there's been more seasonal gain. And so you've kind of offset that, the melt in the discharge. But overall, it's, a lot less ice than there was at the beginning of the millennium, basically. It's not as strong of a downward trend as in Greenland. Greenland is, much starker decline, but this is still a big loss. But the losses are not, it's not uniform across the continent. It's, in the middle of the continent, really not much has changed, and that's not too surprising. It's cold there. There's not really any melt that goes on at the high plateau of Antarctica. There are some places where there's some gains, which again, probably related to more snowfall due to atmospheric circulation and other things. But there's some spots here that are really big losses of ice, particularly on the peninsula, and then this area here, which I'll leave for the moment. I'll talk about that in a minute. And I just want to show, so this is about 135 gigatons per year. Overall, it's lost 2,500 gigatons of ice over the last 24 years or so. And just to give a sense of what a gigaton looks like, it's basically taking a big block of ice and plopping it in Central Park, and it's about over 1,200 feet high, 1,250 feet. So that's 1 gigaton. So you've got 135 of these being lost every year from Antarctica. So it's, in the big global scheme of things, it's not that much, but it is a huge amount of water that is coming off the ice sheet of Antarctica and contributing to sea level rise. As the mass is being lost, we can also look at elevation changes from altimetry. And they basically show very much the same thing that the mass loss is, which is not at all surprising. There are some areas where there's some gains, And then, this big area here. Here where there's big losses, it's a little, the image isn't great, but it's a half meter per year, basically, the dark red. And this is ATL 15 data, I think this is a brand new version of it, version 7. And this paper is just, it's in a preprint right now. It's been submitted to Journal of Glaciology, but it is available online as a preprint.
Would you just point to where Thwaites is?
Well, that was my big
Oh, I'm
thing,
sorry.
but yes,
God.
the Thwaites Glacier area and Pine Island is right here, so that's the area. So I'll talk a little bit more about that in a moment.
So if you lose this ice, do they evaporate into the air or where do they?
So it either melts and runs off into the ocean, or it calves off as icebergs, breaks off and then melts eventually. So that's where the mass is being lost. Either surface, or it can also be, I should say, there's also ocean melt, the ocean heat from the bottom. So thinning of the ice, both from the top and the bottom, as well as dynamic loss from iceberg calving off. Yeah. So it's both of those things are going on.
And is there an estimate now for the number of millimeters of sea level rise attributed to Antarctica versus Greenland or anything else?
There is, I don't think I put that in here specifically. I forget now, but Greenland or Antarctica has not contributed a whole lot to sea level rise yet. But it may in the coming decades for sure, and become a bigger and bigger player. One of the concerns, and exactly how much is still pretty uncertain, but one of the concerns is, better understanding of what the processes are. This is actually, I'm gonna get into your question a bit, was that there was a study back in 2016, which caused quite a stir. Rob DeCanto and David Pollard. Let's see, Amy is asking, no ice at 2 data along the Trans-Antarctic Mountains. Is that like looking back here? I don't know if they got data there or if there. Oh, I see. There's data out. I think maybe they didn't collect data along the mountains there, at least for looking at the ice, the elevation change.
It's the exposure, so I think
Yeah.
they're looking at the ice instead of rock.
Yeah, that's a lot of rock there, so they're not really as interested in that. So I think that's thanks, Dan. So there's a lot of uncertainty, and this paper came out in 2016 that talked about a couple of things that could really destabilize at least parts of the Antarctic ice sheet and the Antarctic coast. And one is called marine ice shelf instability. And basically you have this, the grounded ice, basically the ice sheet, and then it flows out and it floats on the ocean, becomes an ice shelf. And so it's floating on the ocean, so it's subject to what the ocean does. And if you get deep water and warmer ocean waters mixing in there, it's going to thin the ice cover, and that pushes back the grounding line, the line where the ice meets the coast, and it meets the bottom of the land. And so you get this deep water in warm waters melts it back, and you can get to this point where this is where the slope goes what we call negative. It's basically sloping downward. Normally the slope is from the coast outward, it's going down, getting deeper as you get farther into the ocean. This is actually the reverse. And so there's the concern that once you have that, it gets over that hill. Now you've got this warm water almost like drilling into the ice shelf and really pushing back the grounding line much faster and melting things much faster than you otherwise would. So that's the marine ice shelf instability. Then there's what's called the marine ice cliff instability, which is similar. You're melting things back, but you get to this point here where you have this really tall, steep, sharp edge to your ice there, and it's so steep that with the mass of it and the distribution, it becomes unstable and it can topple. I thought of it, or I think of it maybe as like a Jenga, it just becomes unstable. So then you start, sending these big chunks of ice effectively into the ocean where they melt. And so, this would really, speed up the projections, twice the global sea level rise by 2100, which doesn't give you your answer, Florence, but it's twice as much as what they were expecting, which is, yeah, like a half to a meter. I want to say it's like 0.65 meters potentially could contribute if this were to happen. And then 15 meters by 2300, so in the next 300 years or so. So that's, that's a long ways, that's a long time frame, but it's very quick in terms of sea level rise and infrastructure and things like that. So it's definitely something that is a big concern. And one of the reasons it's a big concern is because of the West Antarctic region, which is this region here where we saw these big mass losses. This is a bed map. This is basically the subglacial topography. So this is what it would look like if you lifted off the ice, and just had the land there. And there's been various groups that have looked at this. One of them is this bed machine group. There's 4 now.
Hey, how are you doing, man?
Good. I had to drive over from campus.
Someone needs to mute, please.
Too bad.
Good.
It's working on that big
Hey,
art
John.
project.
Okay.
Thanks for resubmitting your corrected homework. You got yourself a few extra points out of
Yeah,
that.
so I was working with Alex, and then at the beginning of class, I was working.
Well,
with
you should be able to
Yeah.
mute from your
Yep.
side.
Yeah, I heard you two chatting before class started.
So my brain.
There we go. I got it. You got it? Okay, yeah.
Here
All right. So they combine a lot of different data, surface data, on thickness, ice flow velocities, bathymetry. There's a lot of stuff that goes in this. They combine it together. This is where they can kind of look at the surface, and then try to get the topography. But one of the things you see here is, in the blue, this is basically below zero elevation. That means it's below the ocean surface, below sea level. So if you remove the ice sheet, this would be ocean, in this area. And so a lot of the Western Antarctic area where we saw the mass losses are below ground. That's where you get that negative slope because it's, it's below the ocean surface. So yeah, this is a NSIDC DAC data set. And,
I don't think Matthew's model has isostasy involved though, so that's just like where the bedrock is actually sitting, right?
Yeah, well, it uses, and I'm not familiar with all the details, but they did mention the ice velocity as a input source. So they may use that in some way to help figure out.
Right, but if you remove the weight of all the ice,
Yeah,
you'll get rebound.
you would get rebound. Yeah, that's
Right.
a very good point, so this is what it would look like instantaneously when you take the ice sheet off, but then it would adjust over time, so yeah. And so then the bed machine 4, one of the things it does include is this what's called inverse flow perturbation analysis, which and this actually is using the velocity map, according to the paper, and it basically it's using that and other things, and I think almost like some artificial intelligence, I think, but basically to try to get more detail, and yeah, they use the physics of the flow. That's what they said in the paper, the physics of the flow, and then the surface topography to get the bed topography. So that's kind of answering your question, where they use the surface and the variability, the subtle variations in the surface to look at the what's underneath, basically. They do that, like in the ocean, like you can do that for ocean topography and get the if you process the signals and everything, you get actually what the bottom. You can see the mid-Atlantic ridge and things like that. So this gives more spatial detail and finer resolution than what previous products had shown. And again, this has just been published, these papers and the data set. So, so looking at the subglacial topography and grounding lines, like I said, much of West Antarctic lies below the ocean surface. So it's sitting on basically on the ocean bottom, not on land. Yeah, this is kind of recapping what I said before, but this is another product just to show that we have at the NSIC DAT. This is the grounding line, so this is mapping where the actual grounding lines are around the coast and where the ice shelves start. It's a NASA Measures project. There's this negative slope and these instabilities are a particular concern with one large glacier. And it is known as the Doomsday Glacier. Dun dun. And that is Thwaites. And Pine Island kind of gets put in there, they're next to each other, and they both are losing a lot of mass. But Thwaites there's been a lot of research, as I'll talk about momentarily, going on there. And this is, again, zoomed in. You can see the elevation depth there in that region. It's all bluish, which means it's below sea level. And then, again, not a great image at the resolution there, but you're seeing the really strong loss of elevation, the decreasing elevation and thinning that's going on there at the Thwaites and Pine Island. So there is this international Thwaites Glacier Collaboration, ITGC. It's been a huge project, which folks here I know are familiar with to some degree. It's a joint National Science Foundation and NERC, which is a UK funding agency. Big international project, obviously US and UK, but even other investigators from other countries. It's been going on for like nearly 8 years now. And it encompasses a variety of different observations. There's been ship observations, ships going down and taking observations, people going out on the ice camps on Thwaites Glacier, and then airborne measurements as well. And there's not time to go through all of these. But Thwaites has an equivalent of about 2/3 of a meter of sea level rise. Now that's not something that maybe would happen, immediately regardless of these instabilities, but it is a lot of ice there, and it's draining a lot of the West Antarctic ice sheet. So it would accelerate loss from that as well if it were to completely go. So, and there is the NSIC is actually hosts the Science Coordination Office for the U.S. And Ted Scambos, formerly of NSIC, now Series, is the lead, and then Betsy Sheffield here at NSIC is the communications lead. So NSIC has had a pretty big role in this. And Ted and others have gone out and into the field for this over the years as well. And so oh, there it is. I thought I missed one. Okay, so there's been a ton of research. You go to the Thwaites page, and there's just a long list of papers. And I'm not myself familiar with a lot of it, but there's been a lot of kind of breakthrough. And these are some of the, at least that I pulled out that I thought were interesting, relatively recent. One was that the eastern part of the ice shelf seemed to be destabilizing. They started noticing some cracks that weren't there before. These transverse kind of cracks there might be a little hard to see, but there's a couple of big ones there that started opening up, and that's an indication that things are becoming more unstable, and that this whole area could break up maybe even within the next decade. The green X there is where they had this camp that they were taking the observations from. And so, that's bad news. Some good news, Morlingham and others had a paper that looked at the ice cliff instability, and they found that was not very likely. That's something maybe we don't have to worry about, at least not in the near future, in the coming century or so. It may happen eventually, but it's not imminent, which is reassuring. So that's not likely to happen. However, now back to the bad news. There's another recent paper that looking at these subglacial lakes. Like I said, there's channels that they can kind of lose water from or gain. Some of these lakes were like under or right near bordering Thwaites, and in 2013, seven of these drained very suddenly. So you had this big influx of fresh water basically underneath released as much water as Loch Ness in Scotland. No word on whether there was a monster that came out with that or not, but anyways, you suddenly inject a lot of fresh water into the stratified ocean system, saline ocean system. You're going to have a lot of overturning and mixing, and you could mix up some really warm water, relatively speaking, that would increase the melt. And so if this were to continue to happen, you could have enhanced melt from this process potentially. So there's like bad news, good news, bad news, and probably more bad news. But anyways, one of the things that's interesting, this is not regarded to the Thwaites project, and this is as far as I know. I think this is a separate expedition led by the Koreans, but led by South Korea. And going along with them, they're currently on, they took an icebreaker down, they're on a big research expedition down there. And a New York Times reporter and photographer accompanied the cruise, and they've been filing some really interesting reports from down there. I haven't been able to keep up on all of them, but they're currently at Thwaites, and I saw they actually have gotten onto the camp there and are, scientists are trying to take measurements. There's like 40 scientists there, and then they're accompanying and documenting it, taking pictures. So if you have New York Times, worth checking out. So yeah, looking at ice flow, we talked about the ice flow velocities. I just want to show, we do have data from that. These are measures. This is interferometric SAR. So multiple angles from SAR, and over time you can measure the flow velocity and Thwaites. And I forgot to mention Pine Island Glacier is commonly called Pig. I'm not sure if it really likes being called a pig, but that's what's commonly used there. So you can see here the ice flowing down, and you can see the really strong velocities in the purple there in Pine Island and Thwaites. And so you're already losing ice at a relatively more rapid rate than others. But now it's becoming less stable. It's losing more ice than is being replenished upstream. And so that's contributing to the loss of ice. Okay, I got to show a little bit of sea ice. This is, when I look at this is, meters per year. So it's upwards of, 10 kilometers per year or so. As a sea ice person, that's just that's glacially slow. It's kind of boring, but from a ice and glacier standpoint, that's really booking. That's moving quite fast. So now on to the faster moving Antarctic sea ice. The Antarctic sea ice had been for several years increasing to some degree in our satellite data. So the blue is the satellite data, the passive microwave satellite data that we have starting in 1979. And you can see, there's a lot of variability. This is, I believe, in the autumn time period. This is the anomaly. So you can see it's increasing, and with, again, a lot of variability, but you actually reach a record high in 2014. You see this peak there. And so, there was a lot of discussion about, the Arctic is losing a lot of sea ice, but the Antarctic is actually gaining some sea ice. And what's going on? The models indicated that it should be losing sea ice, at least somewhat. And you would expect under global warming conditions that you would be losing sea ice, but it had been gaining sea ice. Well, a couple things happened. First, there was a really nice reconstruction data set by Ryan Folk at Ohio State University that looked at basically some proxy data, atmospheric reanalysis, and other things. And this is a data set that we have here at NSIDC under the NOAA and NSIDC. But this is a recent paper that puts that together, and you can see actually, there was this increase, but there was also a decline earlier, going back to this basically the start of the 20th century. But the thing that really has caught people's attention is that, starting around 2016, there was just a big drop off, and we suddenly lost a lot of ice particularly in the winter, but also in the summer. But the winter maximum has been much lower. We've had record low winter maximums back in 2023. That's that really sharp peak down there, and then nearly as low the last couple of years as well. And so significant losses of sea ice there over the last decade, basically, or since the last decade. And then why is the sudden change happening? There's still a lot of research going on with this, but there's been a few papers out, several by now, really. And one of the first ones, Puritan Dodderidge, looked at the ocean warming being a key factor. There has been some papers that talk about atmospheric changes, the southern annular mode, changing the winds, which controls the ice edge a lot, at least on the shorter term. But it seems like a really key factor is changes in the ocean circulation and ocean warming, preventing the ice from expanding as far north as it normally would. And there's some data there at the bottom, Argo data. These are floats that measure ocean temperature. They only go back to 2004 or so, but there's a pretty strong signal there near the surface where there's warmer waters than there used to be in the previous 15 years or so.
Is the zero, that's the middle of the, in the color bar of the period of record, is that what that?
Oh, yeah, the anomaly,
Yeah.
yes, yeah, I believe that's that's a good question. I'm not sure if it's the full record or if it's like a 30-year climatology period, but
Much to go by, so probably
Yeah.
just the Argo record.
yeah, and then I'm not sure what the Argo that's probably an anomaly relative to the Argo record, the whole time period. Yeah. Okay, getting close to finishing up here, I think, so an interesting thing, this is not so much sciencey related, but I thought it was interesting to show. It's been in the news a bit, looking at the end of an iceberg. The iceberg A23A, it's one of the longest lived icebergs ever, maybe the longest ever, I'm not sure. I mean, at least that we've recorded. We really have been recording icebergs for a terribly long time, but this actually originally broke off the ice shelf, the Filchner ice shelf, way back in 1986. So it's going on 40 years old. It's very much middle-aged. It started out as one of these big tabular state-sized icebergs, Rhode Island size, small state, but 4,000 square kilometers. And then they tend to drift with the winds and the current. They'll drift northward, and this is along the peninsula, and then they'll drift out to into the Southern Ocean and eventually melt away. Well, these are so thick, they're several 100 feet thick, that if they hit a relatively shallow area, they can get stuck there. And that's not a particularly uncommon occurrence that one might get stuck there. But this got stuck there for nearly 35 years. It just sat there. And it just, nothing happened to it. It was just sitting there as basically like an ice island. And then it finally broke free in 2020. It started drifting. It got caught actually in a basically an eddy for a while. So it was kind of spinning in one place for a while. And it's finally now moving fairly rapidly in the warmer waters. And then breaking up. And so this is from September 26th, 2025. And it's now, at that point, about 1,200 square kilometers just after Christmas. This is from Modus True Color. And I actually think I typed that latitude wrong. And this is the correct latitude. Well, this is the updated. So it's actually up, almost to 50 degrees south latitude. So it's getting pretty far north. And this is the latest clear image a month later, a few days ago, January 25th. And you can see there's a lot of these little shards that are broken off and another big piece here. So it's really breaking apart. And you can see here, shows it better, these kind of blue areas, that's meltwater. And it's linear, these striations, and that actually comes from way back from when it was flowing down onto the ice shelf. It kind of, it doesn't flow smoothly. It kind of does this, and gets these little ridges, and so the meltwater kind of pools in there. And the other thing that's interesting is that there's like this, sharp white outline. You can still see it here, and that's the edge of it is basically bowing up a little bit as it's melting underneath. It causes the sides to bow up a little bit. And so it's a lot smaller than it was, started to break up. It's in warmer waters. And so it's probably not going to last too much longer. I'm actually a little surprised it's lasted as long as it has. But it's, these things, they have observed these big bergs going up, up along the coast, almost as, as far as Brazil even. And so, at least Argentina, well into kind of the latitudes of Argentina. So it's not, too surprising that it reaches this far, but it's kind of interesting to see how it's, disintegrating. Okay, so a couple last things. The ozone hole, just wanted to mention that this is not at all my area of expertise, and we don't have this type of data at NSIDC, although other DACs do. But I think it's worth noting because it's been a big story over the decades. It was first observed in the 1980s, and when they were doing satellite measurements, they first thought something might be wrong with the instruments because they were getting really low readings. They were being flagged. There's been some talk of like that they got thrown out and they discarded them, and that's not quite the case from what I understand. It's like, but they were lower than what were expected, and so they were flagged as possibly erroneous. But they had ground measurements that could confirm at Halley Station, a UK station, that things were also the ozone was also low. And there've been a variety of satellite instruments collecting it. So you see this drop below 200 DUs, which are Dobson units, which is a concentration. And the reason for this hole was initially a mystery, like why is this happening? And I mentioned last time Susan Solomon about the book about Robert F. Scott, but she's most, at least in the science world, most known for figuring out along with others, not just herself, but she was one of the lead people that figured out what was going on. It was these chlorofluorocarbons, CFCs from your aerosol cans back in the day, were the cause. These would float up into the atmosphere, all the way up into the stratosphere, and they would interact with UV radiation when it was cold enough. And when it interacted with radiation and was cold enough, you get these reactions where the chlorine would react with ozone, O3, and you form chlorine oxide. I don't remember my chemistry, ClO, and molecular oxygen. And then that ClO would break down again very quickly. It's not a particularly stable molecule. And so then the ClO could break down more ozone. So you had this process that could kind of keep going. And it requires really cold temperatures. That's why it happens in the Antarctic. It also does happen some in the Arctic, but the Antarctic is even colder. So it's more prominent in the Antarctic. And then you also need these like ice clouds that form as like a catalyst or a site for these reactions to take place. So you get these really cool looking, I think John Cassano showed these in his talk. They're kind of really pretty looking clouds, like mother of pearl clouds. But that's what's leading to the ozone loss. Now there's, they put in the Montreal Protocol, expand the CFCs, and the ozone hole is starting to rebuild. So it's a good success story of environmental detective work and understanding what's going on and then addressing it. And then one final thing, recent geological history of the world. We have the ice cores, and we can drill down through Antarctica, now getting below the surface, and the ice cores contain little bubbles that contain little parcels of air, of atmosphere that were there when the snow fell originally. And Antarctica is actually, most of it is a desert. Gets very little snowfall, but over the millennia, hundreds of thousands of years, it builds up. It's built up this big thick ice sheet and captured the atmosphere over the years. And you can core through that. and get a record of climate change going all the way back down to 800,000 years. I think there's an attempt to try to get to 1,000,000 years. But I think I forget where it's, they can get that deep to get 1,000,000 years, but they've gotten to 800,000 years. And you can see the top is the carbon dioxide, and you can see the ice age response there. And then the temperatures showing the ice ages and the interglacials, and then the CO2 comparatively. So, this is, I think, really valuable in terms of understanding climate change and human impacts on change. This long record is showing, the natural changes and then what has happened in recent history with the carbon dioxide and other greenhouse gas emissions. And then one final thing, talking about ice cores. You can drill down and get ice cores. There's the thought, well, can we drill down into the lake and see what's there? And so they did do that and drilled through, and there was a lot of concern about this. This was first done at Vostok, and there was a lot of concern about, what's contamination. How do you do this without contaminating? Because there's the idea, is there maybe some life down there, or what's down there? So they drilled through, and they actually did discover a lot of microbes, surprising number of a variety of microbes, bacteria, even some multi-celled organisms. But they used kerosene fluid as to lubricate the drill, and that maybe it wasn't the best thing to use, and so there was some concern that did they contaminate the sample, because obviously you don't want. If you contaminated, you could be injecting the organisms into the water and then seeing those. But there's been other drillings done more carefully and using sterile drilling methods, and also has found these. So there's this whole kind of little biosphere that happens in these subglacial lakes. These have been covered by ice for, I think, upwards of 15 million years, and these organisms have survived, and you've had this, this food chain and everything that has operated without disturbance. It's pretty remarkable, and it really suggests that life on other planets, even in hostile condition, what we would think of as hostile conditions, may be possible, like Europa, the moon of Jupiter, that has a big thick ice all around with a liquid ocean underneath it, that you could have something like this could survive there. So before I take other questions, this is, I'm sure, the burning question that everyone has. I've talked about Antarctica, but is there any cryosphere in the southern hemisphere outside of Antarctica? Yes. And you have to stay tuned for part 3, episode 3, Escape from Antarctica. So that will be perhaps in March, and I am looking at doing some on-location shooting for that one. So, so with that, any other questions?
So last